lesson today, we have two topics, a real fast one with degree of terms and degree of equations. And most of our time we'll talk about different ways we can classify systems of equations, different things that are going on with them, and that's where we'll get a bunch of new vocabulary. So first, if I want to talk about the degree of a term, that means I need to look at it. Does it have any variables? What are the variables? What are the exponents for just the variables? And add all of those up, and that will be the degree of the term. So if I just take a constant like 2, does it have any variables? So no variables, no exponents. Its degree is 0. Now, if I wanted to, I could also think of that as 2x to the 0. So I could put a variable in there with a 0 on it. X to the 0 is what? 1 times 2 is, so that's still 2. So that's another way of thinking about the constant has degree 0. If I did put a variable in there, the variable would have to have an exponent of 0. Okay, only one term here. What's the exponent? Come on, you guys, wake up. It would be a 3, so that degree would be 3. Okay, this one's a little bit trickier. Your definition said the sum of the exponents. So x has an exponent of 2. What's the power of y? And m and p, and add them all up, and we have, so this one has degree 5. Now, we're not very often going to talk about things that have all these different variables all in one term like that. Most of the time, we'll have things like 5x cubed and 47x. What's the degree of this one? So that much is pretty easy. A little bit more vocabulary. If we start having one of these plus another one, then we have an expression that we call a polynomial. And the degree of the polynomial means find the term that has the biggest degree. So this one, I have 3 terms in it. And think about the degree. What's the degree of the first one, everybody? And the second one? And when I say everybody, that means everybody, not just one person. What's the degree of the -5? So what's the biggest? So this has degree 2. And what do we call a polynomial like that when it's only got x's in there? We've been solving these kinds of equations. We've talked about 3 different ways of solving these equations. We can complete the square, we can factor, and we have a something or other formula that we can use. Quadratic. So if it is degree 2, it is classified as a quadratic equation. And we know sometimes we then talk about those as equal to 0, and sometimes we talk about graphing it. So we do it equal to y. We've seen that. But that's because then on this part, the biggest exponent is a 2. What about this next one? What's my biggest degree? Anybody know the name for a quadratic in one or for not a quadratic, for a polynomial in one variable with degree 3? It's not a quadratic. Anybody know what we call these equations? Cubic equation. If I go slowly enough, you'll get it. Okay, we aren't going to give this one a name because it's got a term that has 2 different variables in it, but what would be the degree of this one? Be careful. How do we get degree of a term? We add the exponents. So what's the degree here? And we have solved quite a few like this. What's this degree? Let's try 1. You add within one term. That's a whole term. And we've been doing a bunch of these where we graph these. What do these graphs look like? Lines. So these are linear equations. So all we needed out of that part was the vocabulary. How do you get the degree of a term? How do you get the degree of a polynomial? And reviewing these 3 terms, linear, quadratic, and cubic. Thumbs up, thumbs down. Does that make sense to everybody? Okay, most of our time today, we're going to talk about linear equations, that last one we just had, so lines, and if we have a system of two of them, how do we classify them? And so far we know several different ways to solve them. We can solve them with substitution, we can solve them with elimination, and we can solve them by graphing. And so let's think for the moment, if we were graphing them, most of the time when you draw a graph of these, you graph a couple of lines and tell me about how they cross. How many places do they cross? How many solutions do we get? Most of the time we get 1 point. So let's get a picture up here of what this outcome might look like. So I might have, I don't know, one line like this, and I might have another line, something like that, and they cross at 1 point. And you just told me that those have one solution, and it's some point. And so we write it as an ordered pair to stress that it's a point. And so this is when we have two lines that cross at 1 point. So make sure you have a sketch kind of like this in your notes and that you've written this underneath it, and then leave some room under it because I'm going to add some other things in here as we go along on this slide. For those two lines to cross at 1 point, would you agree that they must have different slopes? Here I've got one that's negative and one that's positive for them to cross. Could I have had two positive slopes, just different positive slopes? Let's see if I can change one of these lines to show that a little bit. So I could have done something like that, right? And they could both be positive or both be negative, but they have to be different if they're going to cross at 1 point. These happen to have different y-intercepts. Could I have them cross at 1 point but have the same y-intercept? Is that possible? Let some other people take a turn. Is it possible to get the same y-intercept? What do you think, Kayla? What do you think? They could possibly cross right on the y-intercept. So let's see if I can change one of these around. So I could have them cross like that. So they could have either the same or different y-intercepts. So what would distinguish that they just cross at one place would be if they have different slopes, I immediately know they cross at 1 point. So if that's all I need to know, if I have them both in y equals mx plus b form, and I see that the m's are different, I know they're going to cross at 1 point. Maybe I need to solve it, maybe I don't, maybe I just need to know how many places they crossed. Okay, besides two lines that cross at a point, are there any other ways that I could draw two lines? Can I draw two lines that don't cross at just 1 point, Jack? So I could have some parallel lines. So let's get a couple of parallel lines up here. So maybe I've got one that does something like that. And maybe I've got one that does, you guys have better perspective. Do those look parallel or parallel enough on there? So I could also draw those as parallel lines. And how many points do the parallel lines cross out again? 0. So how many solutions? There are no points that make both of those lines true. There are no points that are on both of those lines, so there's no solution for that system. Tell me about my slopes of parallel lines. Same, different, Yesenia? If they're parallel, what do you know about their slopes? For these parallel lines, think about when we're writing equations of parallel and perpendicular lines. What's true about the slopes of parallel lines? Ada? So would everybody agree these have the same slope? Is it possible for parallel lines to have the same y-intercept? The ones that I've drawn there have different y-intercepts. Is it possible for parallel lines to have the same y-intercept? And I see a bunch of heads shaking no. So they must have the same slope and different y-intercepts. When we had one solution, they just had to have different slopes, and it could be either way with the intercepts. But if it's parallel, the slopes have to be the same and the intercepts have to be the same. Okay, if I want to draw two lines up there, is there any other way I can put two lines up there? I think I'll make one of them red and one of them blue this time. Is there any way that I can make them so they don't cross at one point and they aren't parallel? Is there a third possibility of what I could do with the two lines? While you're thinking about that, I'm going to get a first line up here on this graph, changing the colors around as I was saying. So there's one line, and now I'm going to switch colors. So I could draw a line that's parallel. I could put my red line where it's parallel. I could put my red line where it crosses at once. What's the one other thing I could possibly do? I don't want them to cross, and I don't want them parallel. What's the one other thing I could do with them, Griff? I could put my red line right on top of that blue one, couldn't I? In other words, I could have two equations that really mean exactly the same line. They just look a little bit different. Maybe one's got some decimals in it, and maybe one's got some fractions in it or something. But when I graph them, they really end up being the same line. So that's one other possibility that we have here, that they are the same line. And if they're the same line, what about the slope and the intercept? So if they're the same line, they'd have to have the same slope and the same y-intercept. So that's partly why for parallel, it's not enough to just say they have the same slope. Parallel is same slope, different y-intercepts. Same slope, same intercept, they're really the same line. How many points are there that are on both of those lines? When they crossed once, there was just one point that was a solution because there was one point that was on the first line and the second line. How many points are there that are on my blue line and are also on my red line? Okay. Infinitely many solutions. And specifically, any point on the line is a solution. And any point not on the line is not a solution. So you can't just say every single point's a solution. You have to say every point on the line is a solution, because this one over here, for example, is not a solution. So far we've put up there that the lines can be two lines that cross at a point. They can be parallel lines. They can be the same line. We put up there that we can say they have one solution, no solution, or infinitely many solutions. There's some other vocabulary that I'm going to introduce here. First, consistent means it can be solved. It does have solutions. And inconsistent means it cannot be solved. There are no solutions. So this one where they are the same line has infinitely many solutions. So yes, it does have solutions. So it is consistent. Let's go back up to our other pictures. Parallel lines, do they have any solutions? So they cannot be solved, so they are inconsistent. Ones that cross at a point, do they have any solutions? So they can be solved, so they are consistent. So that's another way we can classify these. The last way we're going to classify things would be with these words independent and dependent. And let me actually try to start pulling this up a little bit higher. I'll pull up the rest of the way in a minute. So independent, well, dependent, they totally depend on each other. They are inseparable. You can't tell them apart. Neither one can do anything on their own without the other one. So dependent, they are exactly the same line. So what we just had here in our last picture, these that are the same line, we would classify as dependent. Independent, they each can kind of go their own way. They're okay being separated from each other, at least some of the time. So independent, they are two different lines. So both of these we would classify as independent. So any questions with that vocabulary? That's the hardest part, is keeping those different words straight out of this lesson. Thumbs up, thumbs down. Everybody feel okay with that? Okay, let me move on to some examples then. So we've talked about what these problems would look like if we draw the graphs. Two lines that cross at a point, parallel lines, or ones that are really the same line. Now, most of the time, we've had problems where they say, solve this system. And we just start cranking away with substitution or elimination, and we get an answer. So we've been having ones that cross at one point. But what if they give us a system and we just start cranking away using our substitution or elimination? What might happen to let us know, wait a minute, they don't cross at one point? What might let us know these are really parallel? Or what might let us know that these are really the same line? So take a look at this one, and let's give solving that a try with substitution. Does that sound okay to everybody? So we see it in our problem set, and our first thought is we're just going to jump in and solve it. So we say, oh, well, x needs to be 6 minus 2y. So that means we have 2 times 6 minus 2y plus 4y equals 12. So we have 12 minus 4y plus 4y equals 12. So my y's cancel, and wait a minute. I'm used to, I get y equals something or x equals something. I didn't get that. I got 12 equals 12. So tell me about that. When is 12 equal to 12? All the time? Never? Once in a while? When does 12 equal 12? Always. So we just got something here that is always true. No matter what we pick for x, we can come up with something that is always true. When it's always true, that is going to mean infinitely many solutions, same line, dependent, consistent, all that good stuff. Now, look back at your equations for a moment. Suppose we hadn't actually done this work. Could you look at those two printed equations and take one of them and multiply it by something and get the other one? So that they really are just two different ways of expressing the same equation, that they're equivalent. So Abby, you're nodding your head yes. Which one could I multiply by what? So everybody good? These really are equivalent equations. One's a multiple of the other. So when we graph them, we got exactly the same thing. So something always true, It's going to be the same line. Okay, you can probably guess what's going to happen with the next system. If that one was same line, what do you think this next one's going to end up being? Well, do you think it's going to be one that crosses at a point, or do you think it's going to be the parallel lines? Probably the parallel, just so we can have an example of that. But let's go through the process and see what we get here. And let's do this one, how about with elimination, just since we did that one with substitution. So everybody okay if I multiply my second one by -2? So then I have my first one was 2x plus 4y equals 11. And my second one is -2x minus 4y is -12. So my x's go away. My y's go away. In fact, if I take 4y minus 4y, I have 0. And then on this side, I have what, -1? Now, when does 0 equal -1? So this one is never true. So there's no way to get something true. There are no solutions, which means these have to be parallel lines, which means they need to have the same slope and different y-intercepts. I wonder if I could look at these equations. I could say the first one is 4y equals -2x plus 11 and divide everything by 4. And I could take the second one and say 2y is -x plus 6 and divide everything by 2. Do I get the same slope? -2/4 and -1/2, are those the same? Do I have the same y-intercept? So same slope, different y-intercepts, that means it's parallel. Anybody with questions on that? Okay, a lot of your problems are going to look like this, and they're going to say you need to do a whole bunch of things in this one little box. You need to solve it. So if there's a solution, you need to get that ordered pair. And you need to say how many solutions. Was there one, infinitely many, or none at all? And you need to say consistent, inconsistent. And you need to say whether it's dependent or independent. And you need to draw a sketch. So let's get one of these up here where we've actually gone through and we have done all of that. So first thing when I start looking at that, it's like, well, let's just jump in and try to solve the thing. And what do you guys think? How many think substitution? How many think elimination? Okay, that's where most of the hands are. So what do you want to, tell me what to multiply? Yo-Yo, which one should I multiply by what? So I'll multiply the top one by -3 and make sure I get this right. -6x minus 9y is plus 18. Did I do that right? And so now let's solve that. The x's go away. 9y is 0. So what's y? So if you get down to x or y equals a number, that means that you have one solution. If you get 3 equals 3, that's always true, or 3 equals 5, that's never true, then you know you either have infinitely many solutions or no solutions. But if you get a number for one of them, you automatically know that you have one solution. We know that the y is 0. So everybody take 0 and plug that in for one of these y's and tell me what we are going to get for the x. So pick the first or the second equation, whichever one you like best, and figure out what x needs to be. Leah, you have an idea for x? -3, thumbs up, thumbs down. So if we do plug the 0 in right here, we have 2x has to be -6. So x would indeed be -3. So here is our solution. So out of our list of directions, so far we have solved the system, and we've classified it by how many solutions it has. Okay, if it can be solved, if it does have a solution, is it consistent or inconsistent? So we write down that it is consistent. And we've done that classification. And we said independent and dependent. They're independent if they're two different lines. Do we have two different lines if they cross at one point? Yeah, we've got two different lines. They're not the same line. We've got two different lines that cross at one point. So they are independent. All that's left is to draw a sketch. And on these sketches, I need you to think about it a little bit. We're not doing a real, totally accurate graph, but I do want it to reflect the slopes of the lines. And if you have a solution, get it in the right quadrant. So the position of the solution, if there is one. So we know that -3, 0 is where they cross. So my graph better have them cross on the negative side of the x-axis. So I need to go through that point. Now I just need to figure out, did I have positive or negative slopes on these things? So my top one, I had 3y is -2x -6. Positive or negative slope? And my bottom one, I had 18y is -6x -18. Positive or negative slope? So one's got a slope of -2/3, one has a slope of -1/3. So different slopes, but both negative. So I simply need to draw so that they cross here, and they have two different negative slopes. I'm not really worrying about the scale on the y-intercepts, just that they're both negative, one steeper than the other, and they go through -3, 0. Questions from anybody on today's material? I know that was kind of a lot.